Next thing we need to talk about is the idea of an identity matrix. So an identity matrix is always a square matrix. It has ones along the main diagonal. So we'll draw a picture in a minute of what that looks like. It's got zeros everywhere else. Okay, so let's start with the simplest case, the 2 by 2 identity matrix. 2 rows, 2 columns, so it's a square matrix. The main diagonal, that's the diagonal that starts at the top left and goes down to the bottom right. So there's ones along that main diagonal, zeros everywhere else. The 3 by 3 case is always an important one as well, something that we often run into in practice. So 3 rows, 3 columns. We've got ones along this main diagonal that goes from the top left to the bottom right. And we've got zeros everywhere else in that matrix. So there's our 3 by 3 identity matrix. Now, if we think back to real numbers, if we grab any real number, like say 7, and we multiply it by 1, yep, we still get our original number, 7. And even if we did this in the other order, if we did 1 times 7, yeah, we'd still get 7. So the number 1 here plays a special role. It's called the multiplicative identity when we're talking about real numbers. And our identity matrix, I plays the role of 1 when we're talking about matrix multiplication. So here's what we mean by that. If we take any matrix A and we multiply it by the matrix I, we just have to choose the appropriate I so that the sizes are compatible. We end up with the original matrix A. So sort of the same property as 1 had with the real numbers. Grab any real number, multiply it by 1, you get your original real number back. So we take any matrix, multiply it by I, we get our original matrix back. And the order here of this particular multiplication doesn't matter. So if we take the identity matrix times A in that order, we get our original matrix A. So this is true for any matrix A. Okay, this is a fact that we'll come back to a little bit later on when we're using matrices to solve systems of equations. So for now, we'll just store this fact away. Come back to it a little bit later. And now we need to talk about the idea of inverses of matrices. So let's take a square matrix A. Square meaning same number of rows as columns, so it could be 2 by 2 or 3 by 3, etc. We're going to look at the matrix A to the negative 1. Now when we read this, we call it the inverse of A. So the inverse of A has the following properties. If we take A times A inverse, we get the identity matrix. And if we do the calculation in the other order, if we did the inverse of A times A, we still get the identity matrix. And as I pointed out a little bit earlier, A to the negative 1, when we see that symbol, we read it the inverse of A. So if we take a matrix A and we multiply it by the inverse, this inverse matrix comes along and undoes A and gives us the identity matrix. And remember, we pointed out before that the identity matrix plays the role of 1 for matrix multiplication. So this sort of reminds us of the idea that if we take a real number, multiply it by its reciprocal, then we're getting 1. In other words, we could say the reciprocal of 7 undoes multiplication by 7. So let's check that the matrix 3, 1, 5, 2 is the inverse of the matrix A, which looks like 2, -1, -5, 3. All right, well, for the purpose of this calculation, it will be handy to give this matrix here a name. So let's maybe call it B. So we're going to check that the matrix B is the inverse of A. Okay, well, there's two things we need to check. We need to check that if we multiply B times A, we get the identity matrix, and we need to check the multiplication in the other order as well. So we need to check B times A times B, make sure they both come out to the identity matrix. So let's try it. B times A it's going to look like this. We'll circle the rows of our first matrix and the columns of our second matrix, and we're going to build some dot products here. So row 1 dot column 1 is going to look like 1. Row 1 dot column 2, 0. Row 2 dot column 1, 0. Row 2 dot column 2, 1. Okay, so that's the identity matrix. That's good. That's exactly what we were looking for. We want to make sure that B is undoing A. And we want to make sure that this is still true if we multiply our matrices in the other order as well. So this time we'll do A times B. So let's circle the rows of our first matrix, columns of our second matrix, and we'll build our dot products. So row 1 dot column 1 looks like 1. Row 1 dot column 2, 0. Row 2 dot column 1, 0. And row 2 dot column 2, 1. Yes, perfect. That comes out to the identity matrix as well. So we've checked the two things, and so we could now say, yeah, B is the inverse of A. So often we could say, okay, we've found the inverse of A. It is the matrix 3, 1, 5, 2. So we'll explore matrix inverses more in our next few videos.